Since we're talking about the acceleration due to gravity, let's take a look at free fall and again at air resistance. We know from last chapter that all objects, regardless of their mass, fall at the same rate. This is known as the acceleration due to gravity, and it's negative 9.8 meters per second squared. We always ignore air resistance in our problems, but that poses the question, what if we didn't ignore air resistance? When we look at the difference between an elephant and then I think that's a mouse, elephant has a much greater weight, or the force of gravity. It's 10,000 newtons approximately. When I look at the force of gravity or the weight of a mouse, it's 10 newtons. So they have very different weights or very different forces of gravity. But their masses are also very different. The elephant is 1,000 kilograms. The mouse is only 1 kilogram. So their acceleration is the same. Even though their forces are different, because their masses are different, their acceleration is the same. So when I look at the difference between an elephant and a feather, and what effect air resistance will have on falling objects, there are three things that determine air resistance. And air resistance is just a contact force that results in the collision between the air and the object. The first one is air density. Okay? Density refers to the amount of particles in a certain volume. So it makes sense that if the air is more dense, there's going to be more drag or more air resistance. We often refer to air resistance as drag. The cross-sectional area of the object. If you see somebody skydiving and they're wearing one of those squirrel suits, if they spread their whole body out like a starfish, they're going to have more area, which gives more air resistance. If they combine up and roll into a ball, there's going to be less air resistance. And the last thing that affects air resistance is the speed of the object. As an object is falling, it's speeding up. Its velocity is increasing. As the speed of an object is greater, the air drag also increases. So if I increase air density, increase cross-sectional area, and increase the speed of the object, that's going to increase the air resistance. So what will happen to an object is because the drag changes, it would continue to increase as you speed up, and we already know that as I fall, free fall, I increase in speed. That's going to increase my drag until there's a point, just like you can see in the animation, where the drag, as it becomes larger and larger and larger, is going to equal the weight of the object, or the gravitational force. When that happens, the object reaches terminal velocity. What that means is that the change in velocity terminates. In other words, it stops accelerating. And we call that velocity the terminal velocity. So if we include air resistance, our problems become a little bit more complicated. We know that air resistance will slow an object down. So its acceleration, although it starts at negative 9.8 when it's in free fall, will decrease and decrease and decrease as that air drag increases until we reach a terminal velocity. So those are just a few of the applications of Newton's laws that we will be developing in class.